All right. Well, those are the diagrams. Stable spiral sink. If the eigenvalue were to be have a real positive part, then it'd go out from the origin instead of in. If the eigenvalue has zero real part and only imaginary part, we get circulation, pure circulation. If the eigenvalue is repeated, there's only one eigenline to follow. If it's positive, it's out of the origin. If it's negative, it's into the origin. And then if you have two eigenvalues that are different, you could get sinks, sources, or saddles. That's your family of mugshots. All right. And then the last thing I want to talk about is organization. What we've done, we've taken this matrix ODE problem that's rooted in eigenvalues and eigenvectors, and we've now just classified it into 8 typical mugshots. Okay? Those mugshots are tied back to the eigenvalues. But you might remember that when we calculated the eigenvalues, I had brought up traces and determinants. So, if the eigenvalues dictate the type of phase diagram, then let's remember that the eigenvalues are determined by trace and determinant. Thus, the phase diagram is determined by trace and determinant. Let's remind ourselves. The trace of the matrix A, I will write down as capital T, or your book will use the Greek letter tau. I'll clean this tau up a little bit. Vertical line, and then a top with a little curl on it. There's my tau. And that is A plus D, the sum of the main diagonal elements. Yeah, supermassive black holes are stable spiral sinks. Crazy, didn't ever think about that. All right, and then the determinant, which is D, in your book is represented by a delta, and it's going to be the typical way to calculate determinant. So what that means is that if I look at the determinant of A minus lambda I, that's going to be lambda squared minus the trace of lambda plus the determinant. I'm going to set that equal to 0. But that's just a quadratic equation. I have a formula for that quadratic equation, and that formula is that lambda, you should be equal to negative, well, there's a negative trace hanging out there, plus or minus the square root of negative trace squared minus 4 times determinant all over 2. And so I get trace plus or minus the square root of trace squared minus 4d all over 2. So where am I going with this? The idea is that lambdas tell us the picture. And what I want to know is, if you give me a system without having to calculate all the solution, can I get an idea of what picture the system makes? Well, I can, because lambda is a function of trace and determinant. So what I'm going to do is I'm going to set up a plane. This plane is not the phase plane. This plane is a plane to just organize the information. And on the horizontal axis, I'm going to put trace. And on the vertical axis, I'm going to put determinant. And now I'm hoping, well, first I notice for every single point, like this point right here where the tip of the cursor is, at the tip of the cursor, there's some trace value and some determinant value. Let's say 2 and 3. But if you know trace is 2 and determinant's 3, you know all that stuff. But if you know all of this, then you know the eigenvalue. But if you know the eigenvalue, then you know the picture. Okay? So my hope is that The eigenvalues with respect to trace and determinant are very well organized, and we'll talk on Monday that organizational structure, but it turns out it is absolutely organized. In that plane, if your trace is positive and your determinant's positive, you are some sort of source. If your trace is negative and your determinant's negative, you're some sort of sink. And if your determinant's negative, you're some sort of saddle. And so that means that I am capable of understanding only the trace and the determinant, and then boom, I instantly have a picture associated with the system. That's what we're going to look at next time.